Is that true? Let's check. So I go back to R, and then I compute the autocorrelation of data V. And you see, there is almost no more periodicity. There is random fluctuation around 0. Well, there is still some periodicity, now negative, after a delay of 1 year. And this means that our deseasonalization procedure was not completely effective in estimating seasonality. So after 1 year, the estimate was exaggerated a bit. But anyway, this kind of autocorrelation function doesn't tell you clearly that there is seasonality. There is some, you can recognize some fluctuations that are not really random. It could be a weekly cycle. Sometimes you see in river flows weekly cycles. And at the beginning, when I started analyzing river flows, I thought, what's the reason for the weekly cycle? And then I understood that the explanation for the weekly cycle is due to the human activity, to the impact of human activity on the river. So basically, during the week, you have withdrawals, maybe for the presence of hydropower production, or for the presence of irrigation, or for the presence of industrial withdrawals. During the weekend, you have less withdrawals and more releases, because people wash the suits and wash the houses, and also they have longer, let's say, more substantial meals, and they wash the dishes after the meal. And then if you have a discharge in the river of the sewer system, maybe after depuration, you get an increase in river flows. So the weekly cycle is there, and it's due to the impact of human activity. Very often it's not so recognizable, but here it could be a weekly cycle, I'm not sure. But let me make a comparison between the previous autocorrelation and this one. You see that in this one, you have only small exceedances after, let's say, outside the blue bands. The blue bands are the confidence bands of the zero value. So you have a correlation that even when it is significant, is very reduced. If you go back to the previous one, you see that you are well outside the blue bands for the impact of seasonality. So it's fine. I think our deseasonalization procedure was successful. Okay, now that we deseasonalize the data, we are ready to estimate our autoregressive model, which is very simple to do. Let's go back to our code. First of all, I am taking the longest way to estimate the autoregressive model, because there is an R function that does it. I'm not using the R function, because the R function, it's not transparent. I just want to use with you the same procedure, manual, let's call it, that I introduced during the lectures. Okay, so what I'm doing here, let me copy and paste this instruction. What I'm doing here, I created a new vector, which is a replica of the deseasonalized data, but it's shifted forward one step. You see, I added a 0 at the beginning, which is the mean value, and then I cut an observation at the end. So I just moved forward the vector one step. So far you don't understand why I'm doing that, but you will understand in 2 minutes, okay? So for now, it's just important that you understand that I simply shifted it. Fine. Let me go back here, and then there is, I define a trial value for phi1. Let me define, sorry, phi1. Let me define it as equal to 0.1. Now, let me compute the residuals. And better, let me compute the sum of squares of the residuals. And I use I define a function to do that. I'm cutting and pasting. So let's try to understand what is doing this function here. You see that I compute a vector which is given by the data minus phi1 times the shifted vector. The shifted vector is just xt minus 1. So I'm computing for each of the observations, I am computing xt minus phi1 xt minus 1, which is epsilon. I am computing epsilon for each time step with a simple operation between vectors. And then I give back the sum of squares. Because you see that I computed the residuals, I squared them, you see a square, and then I summed the vectors. So I computed the sum of squared residuals. And you can guess that this is the objective function that I am using to estimate the correct value of phi1. I called it phi here. Okay, I'm cleaning the screen now. And let me go back to the code. And here you see that I am using an optimizator in this instruction to compute the optimal value of phi autoregressive parameter. And this optimizator is not the same that we used before. We used DE optim before, and I'm using here optim, which is embedded in R by default. It's not as powerful as DE optim, but still it's a solution that can be used. You see that I get a warning because it says, look, it's not really reliable what you did. But anyway, so let me see PR2. This is the resulting value for phi1. You may do the same with the EOT. It doesn't change much. Sorry, you get another one. What is your value?
0.36.
36. There is something, I think, and you just copied and pasted my instructions.
Yes, and I see also that the plot was different.
Sorry, what?
The plot was different.
Not sure. You could try with DOptim and see, because you have this function which gives to you, which can be used also with DOptim. Okay, let's make this check. Let's try to use DOptim, okay? And I think I didn't keep it. Let me see if I have. Not sure. Yeah, I have it. So basically, I told you that when you install software, you have to load it every time that you start up. So let me see if I do this. I think the instruction should be DOptim. And I need to go back to see how I define the function. Yeah, I think that's okay, lower and Yeah, I still get 0.6290, and it would be interesting that if you... Yes, yeah, just 1 second. Again, 0.36. Okay, there is a mistake, of course, and we have to find it. Sorry? So what is the result for all of you? It's mine? Yeah. And what about you? The same mine? Yeah. So I think there is something probably... The plot of the data is fine. Could you find the same autocorrelation function? No. So, if you're not successful in finding the mistake, I can, okay, just try to have a look when you're safe. Okay, very good. Okay, so basically we found that the value of the parameter, which is what it's important for us, is 0.6129, etc. Okay, let me go back to the code. Now I have to compute the residuals, and okay, let me just go back to the computation of PR2 with the opt-in, because so I avoid to, okay, and because I need to get the result of the best value for phi1 in just one variable, like in this case. Okay, so now compute the residual, epsilon, they are called, which is, they are simply given by data minus PR2, which is the best value for phi1, multiplied by data dd, which is the shifted vector. And these are the epsilon. And let's plot the autocorrelation. If I don't specify any lag, I just want to show you what happens. You get the autocorrelation up to a lag that is decided by R by default. And it's basically close to 0.1. And you see that the autocorrelation function is indeed what we would expect if the model works well. Because you have the first autocorrelation coefficient, which is 1 by definition, but then we have all the coefficients that are within the blue band, which is the confidence band of the zero value, and only a couple of coefficients, I could say one, are outside outside the blue bands, but I told you that we can tolerate about 5 values over 100 of outside coefficients, still accepting the validity of the hypothesis. So it's not a problem if we get one coefficient here that is falling outside, and basically my conclusion is that the residuals are independent. So the model works fine. Okay, back to the code. Okay, here you have an application of the Kolmogorov-Smirnov test. Just skip it because I didn't introduce the test to you. It's in the slides, but I decided this year to forget about it. And then we can turn directly to the generation of synthetic data. In this case, I am using the R function. So I could easily generate the synthetic data by doing step by step what I did in class, but I am using the R function because I want to teach to you the R function. If you like, after generating with the R function, we can make the generation manually, as I explained in the class. It's not a problem. So let me compute this. Let me, copy this instruction in R, and then I am explaining to you what it does in detail. Okay, you see that the generation was very quick. First of all, the function is called arima.sim. I already introduced this name during my lectures. The first argument of the function, the simulation function, is the length of the data vector that you want to generate. And given that the text required to generate 50 years of data, my length is 365 times 50. Now, the second argument should be a description of the model, because this function is able to generate from whatever ARIMA model. We are generating from an AR model. So we have to tell the function what kind of model we are proposing. And basically, there are many ways to tell the function what is the model type. The easiest in this case is to provide a list, and you don't know, I think you don't know yet what is a list in R. I will define it in 5 minutes from now, but for now let's say that the list is a group, a pool of information, a cluster of information. Okay? In R, you can cluster vectors, cluster variables within a list. And the information can be in a list numeric or alphanumeric. Alphanumeric means characters. So let's, for now, take into account and let's assume that the list is a collection, a cluster of information. So the function here, the simulation function, needs a list which describes the model. And you see, in fact, that the argument is model equal to, and then list. Basically, I am telling the function that the model is defined through a list, as he wants. So, the only argument, the only information that I'm passing to the list is an information called AR, by definition of the function, which is the autoregressive coefficient. And in fact, I am telling him AR equal PR2. PR2 is my phi1 value. So basically, I define the model through a list. In this case, I just include included in the list the value of the autoaggressive coefficient. Okay, and then I should give to the function the vector of the epsilon, and this vector is to be called in the function, it's an argument that is called inov or inov, I and nov, and I am generating this vector right now. It's a normal vector, R norm, which is as long as the length of the simulation, 365 times 50, has mean 0. In this case I put mean epsilon, but epsilon I didn't make the check, but epsilon has mean 0. And the standard deviation of this epsilon is equal to the standard deviation of my previously computed epsilon. So I am generating an artificial epsilon with the same mean and same standard deviation of the previously computed epsilon. This is what I need. Okay, let me spend some more words on the list. The list would be, for instance, here 10, or let me see, trial, equal list. Let's make an experiment. I'm just making an experiment. And the list would be A equal 2, B equal 3, and C equal C plus D. This is alphanumeric. You see that I am defining a list with 3 information, which I call A, B, and C. And the first 2 information is numeric, the last one is alphanumeric. Let me see, okay, it's fine. R accepted it. And how does it look? If I now write trial, this is the result. You see, it says that you have a first information in the list. The information is identified through a dollar sign, which is A, it's numeric. A second information, which is B, it's numeric. A third information, which is C plus D. And you may get any single information in this way. Trial, dollar sign A, 2, trial, dollar sign C, C plus D. Because one other thing that I probably didn't tell you is that you can define alphanumeric variables in R. You can write A equal my name. You just have to use commas, and that's fine. Of course, you can make operation with the alphanumeric variables. If you make A times 2, you get an error. But you can put information together in a list. This is useful because sometimes you may have the need to put together some variables in order just to remember that they are related. And being able to put together in a list numeric and alphanumeric variables is a good option. So let me go back to the instruction for generating the data. Basically, if you look at the help, you can find any explanation that you need. You see there is arima.sim and there is model. The first argument is model. I used it as second argument, it doesn't change if it is identified. And if you look at the help, it says model a list with component AR and or MA, giving the AR and MA coefficient respectively. Optionally, a component order can be used. An empty list gives an ARIMA 000 model that is white noise. White noise means independent data. Okay, basically, we already identified already generated our data, and now we have to add the seasonal component back. And this is the instruction, which is simple. S data, which means synthetic data, are equal to the deseasonalized synthetic data multiplied by the standard deviation, seasonal standard deviation, and then the seasonal mean is added. Okay. Now we are done, and let's try to have a look at this data plot. That's data type equal line. Here they are. And basically they look quite similar to the original data. There is a difference, which is the length of the series, of course. It's 10 times longer, and given that it's so long, you can't easily recognize the peaks there, the seasonality. But if you draw the autocorrelation function, you see that it's similar to the previous one. This is the autocorrelation function for the simulated data. Okay, now we can compute the flow duration curves. First of all, let's keep in mind that we have to estimate uncertainty, the standard deviation. So we basically have to estimate 50 annual flow duration curves. Not just one, which can be estimated by pulling the data together. We have to estimate the 50 annual curves. So first of all, here, let me define an array which has dimension. I go back in R, has dimension 50, 365. And this array will contain the individual flow duration curves. Okay, that's fine. Now, let me go back to the code. And here you see a force cycle between 1 to 50, and the purpose of each run of the force cycle is to compute for each year the flow duration curve, the individual flow duration curve for that year. And basically, let me copy and paste the force cycle, and then I comment in R the result. basically, okay, the fourth cycle is repeated 50 times and the index of the cycle is I. So it is defined a variable that is called PR3, which is rewritten every year, and this variable is obtained by using two functions. The first function is REV, and the second function is sort. Sort is ordering the data in ascending order. REV is reverting the order of the data because I want the descending order. There is also the way to tell the function sort that you want the data in descending order. I don't know how to do that. If you consult the help, it's easy. Basically, what I'm ordering are the synthetic observations in each year. And in fact, you may remember, the synthetic observations are called S-data. And you see that for varying I, you get the data in the first year, second year. For instance, what happens if I is equal to 1? Then the index in the vector is I minus 1, 0, times 365, 0 plus 1. So the first index is 1. The second index, if I is equal to 1, is 365. So at the first round of the fourth cycle, you get the data from 1 to 365. In the second run, you get from 366 to 730. So every run you get the data in each year. And then you sort them and revert them. And when you are done, you assign the resulting PR3 values to the array FDC. For varying I. So every year you compute the flow duration curve and you put it in the FDC array. And then you go back next year and you put it in the FDC array. And in doing so, I easily computed the 50 flow duration curves. Okay, good. Just 1 second because I have some updates. Okay. Now, let's plot them. And the way I'm plotting them, it's this one. Basically, I create a basic plot, and the basic plot is a plot that has on the abscissa a sequence from 1 to 365. And in the ordinates, I put the first flow duration curve. Type equal to line because I want a line to draw the flow duration curve. And then it's safer to put a limit on y, because y is the ordinates and the river flows are displayed there. So if in the first year you have a low river flow, then the plot is created by adjusting the ordinates to the low river flow, and the subsequent flow duration curve may go outside the graph. So it's better to specify to R that the limit for y is between 0, because we don't need negative y's, to the max of all the flow duration curves, the max of the synthetic data. And then, by using a fourth cycle, I add the single lines of each flow duration curve. This is what you can see there. And now, of course, it's interesting to see the result, but let's wait a bit to digest what has been done. Okay, let's see the graph. Here they are. Sorry?
I have only just one line.
Because probably did you use the paragraph after lines, the instruction lines? Because I tried to better explain. I think you didn't press enter here. Try to go back to the console. Okay, fine. These are our flow duration curves. Of course, we should compute now for each value of the duration, the mean, and the standard deviation to estimate uncertainty. I think it is not done here. Let me see. I think, yeah, because you know, it's the last instruction that is given here is a check to remove negative values, because I didn't make this check.